Right now, your hand is resting on something solid. Or so you think. Physics says otherwise. The desk, the floor, your own body, none of it is solid. Every atom inside you is over 99% empty space. And beneath that emptiness, there are no tiny balls of matter. There are only invisible fields. Vibrating, everywhere, always, will go from the boiling energy of empty space to the field that gives everything its weight, to a math proof that says particles as solid objects simply cannot exist. If this pulls you in, subscribe. More of this coming. Now, pay attention. We begin. Pick up anything near you right now. A phone, a cup, a table edge. You feel it. Solid, firm, real. Your brain tells you contact is happening. Physics tells a completely different story. Your hand never actually touches that object. Not even close. Here is what happens instead. Every atom in your fingers contains a cloud of electrons spinning around a tiny core. Every atom in that cup or table has the same cloud. When your hand gets close enough, those electron clouds meet. And electrons carry a negative electric charge. Same charges push each other away. Hard. What you feel as solid resistance is just two invisible electric forces screaming at each other across a gap so small it makes a human hair look like a highway. No part of you ever makes physical contact with the world around you. The sensation of touch is the sensation of repulsion. That already sounds strange. Hold on, it gets stranger. Now ask yourself this. If atoms are mostly empty space, and if the only thing creating the feeling of solidity is a force between clouds, then what are objects actually made of? The answer that modern physics landed on shook the entire scientific world, and most people have never heard it explained properly. Objects are made of fields, invisible, continuous fields that stretch across every corner of the universe. Every particle you have ever learnt about in school, every proton, every electron, every photon of light is a ripple in one of these fields, a temporary pattern of energy in an ocean you cannot see. Think of it like this. Drop a pebble in a still pond. A wave spreads outward. That wave is real. You can measure it. But it is made of water. It has no separate identity from the pond. If the pond disappeared, the wave would vanish with it. An electron works the same way. It is a ripple in the electron field. It only exists as a disturbance in something much larger. Without the field, the electron is nothing. Scientists confirm this framework through decades of experiments. It is called quantum field theory, and it is the most precisely tested idea in the history of science. Its predictions match measurements down to an accuracy that would be like predicting the distance from New York to Los Angeles and being off by less than the width of a human hair. So why does the world look the way it does? Why do chairs look solid and rocks look hard if everything is just ripples in invisible oceans of energy? Because when you get trillions and trillions of these ripples bundled together and vibrating in sync, their quantum weirdness averages out. The chaos of the tiny scale disappears under the weight of sheer numbers. What's left looks, feels, and behaves like a solid object. But zoom in far enough and the solidity dissolves. All that remains are patterns of energy doing what fields do, vibrating, interacting, pushing and pulling across invisible distances. Your desk is not made of stuff. It is made of motion. You just felt something solid a moment ago. Now you know that feeling is your fields reacting to another set of fields. The universe is more process than object, more verb than noun, and that desk is one of the simpler things to explain. Because once you understand that particles are just ripples in fields, a question immediately follows: what exactly are these fields? How many are there, and what happens inside them? The answer changes everything you thought you knew about matter. A single atom is overwhelmingly empty. Not a little empty, overwhelmingly, absurdly, almost completely empty. Here is how to picture it. Imagine an atom scaled up to the size of a professional football stadium. The nucleus, the dense core at the centre, would be the size of a marble sitting on the 50-yard line. Everything else inside that stadium? Air, nothing, emptiness. The electrons do not fill the rest of the space. They occupy a fuzzy cloud at the outer edge of the stadium, more like a thin mist than a solid wall. That is the atom, mostly void. Now think about your body. You have roughly 7 billion atoms in you, 7 followed by 27 zeros. Every single one of them is built the same way. A tiny dense core, an enormous amount of empty space, and a thin cloud of electrons at the boundary. If you could somehow squeeze out all the empty space from every atom in every human being on Earth, every single person alive right now, the remaining matter would fit inside a sugar cube. A single sugar cube. That is what you are actually made of. So why do you feel solid? Why do buildings stand up? Why does concrete crack your skull if you run into a wall? The electron clouds at the edge of every atom carry a negative electric charge. When two atoms get close, their outer clouds repel each other with enormous force. That repulsion creates the sensation of hardness. The wall does not stop you because it is solid. It stops you because its electron clouds refuse to let yours pass. And here is where it gets really uncomfortable. The nucleus in the center of every atom is itself mostly empty space too. A proton, which sits inside that nucleus, is made of even smaller pieces called quarks. And the quarks are bound together by a force so intense it makes nuclear explosions look gentle. But even inside the proton, the quarks themselves are tiny, and most of the proton's volume is just the energy of the force holding them together. So zoom in as far as physics currently allows. At every level, there is almost nothing there. What fills the space? Fields, the forces and fields that ripple through the empty interior of every atom, are what give it structure, energy, and behavior. The atom is less like a miniature solar system and more like a standing wave pattern, a stable shape made of energy and force, held in place by rules we are only beginning to fully understand. This picture collapsed the old model completely. For centuries, scientists pictured atoms as tiny hard balls. Then they discovered the nucleus, then the proton, then the quark. At each step, what seemed solid dissolved into something smaller and stranger. And at the deepest level accessible to experiment today, there is no solid floor. There are only fields and their ripples. Every solid thing you have ever touched follows this same logic. The chair you are sitting on, the ground beneath your feet, the bones in your hand, all of it traces back to mostly empty space organized by invisible forces. Your entire physical world is a carefully arranged void. And if atoms are mostly nothing, and if particles are just ripples in fields, the next question hits like cold water. What exactly is a field? How does something invisible and continuous create everything you can see, hear, and hold? That answer goes deeper than most people expect. Close your eyes for a second and picture the universe. You probably see planets, stars, galaxies, maybe some dust drifting between them, objects floating in space. That picture feels natural. It is also incomplete in a way that changes everything. The universe is not a collection of objects floating in empty space. It is a set of fields filling every point of space, from the inside of your kitchen to the edge of the observable universe. Objects are what happens when those fields get disturbed. A field, in the physics sense, is something that has a value at every point in space. Temperature is a simple example. Every point in a room has a temperature, even the empty air in the middle. Gravity works the same way. You feel it everywhere on Earth, even in open sky, because the gravitational field fills that space. Quantum fields follow the same logic, but go much deeper. There is an electron field that stretches across all of space-time. One single field, everywhere, always, every electron you have ever heard of is a vibration in that field, a localized pulse of energy that carries the properties we label as electronness, its charge, its mass, its spin. Remove the vibration and the electron disappears. The field itself remains. The same goes for every other fundamental piece of matter. There is a quark field, a photon field, fields for particles called muons and neutrinos and gluons. Each one is its own invisible ocean, and each one covers the entire universe simultaneously. Think of a guitar string. When you pluck it, a wave travels along it. That wave is real and measurable. But the wave and the string are inseparable. You cannot take the wave out of the string and put it in a box. Particles relate to their fields the same way. They are the wave, and the field is the string. This framework, called quantum field theory, was built through the 20th century by a series of breakthroughs. Scientists kept probing smaller and smaller scales. Every time they found a new particle, they were really finding evidence of a new underlying field. The particle was the announcement. The field was the discovery. What makes this idea so powerful is its precision. Quantum field theory predicted the behavior of the electron to so many decimal places that checking the math would take years by hand. Experiments confirmed every digit. No other scientific theory in human history has achieved that level of accuracy. So the universe is less like a box of objects and more like an ocean of overlapping fields, each one active, each one buzzing with energy, each one capable of producing ripples that we call particles. And here is the part that should make you pause. These fields do not sit quietly waiting to be disturbed. They are always active. Even in the emptiest region of space, every quantum field is doing something. Humming, fluctuating, never fully at rest. The universe has no off switch. Now, if particles are just ripples in fields, and fields never stop moving, you have to ask, where do particles come from in the first place? Why do some ripples turn into stable electrons, while others turn into photons or quarks? The answer involves a rule that governs every field in existence. And that rule leads directly to one of the strangest ideas in all of physics. Every particle you have ever heard of is born the same way. Energy concentrates in a field. The field responds. A stable ripple forms. That ripple carries specific properties. Scientists detect it. They call it a particle. That is the whole story. Particles are what fields look like when they get excited. Picture the surface of the ocean on a calm day. The water stretches flat in every direction. Now a storm rolls in. Waves appear. Some are small and quick. Some are tall and slow. Each wave has a shape, a speed, a size, but every single wave is made of the same thing, ocean water. The waves are real. You can measure them, surf them, track them, but remove the ocean and every wave vanishes instantly. Particles work the same way. An electron is a wave in the electron field. A photon is a wave in the electromagnetic field. A quark is a wave in the quark field. Each field produces one type of ripple, and each ripple carries the signature properties of that field. Why does every electron have the exact same charge? Because they are all ripples in the same field, governed by the same rules. You would not expect two waves on the same ocean to follow different laws of physics. Same field, same rules, same properties. Every time. This explains something that always seemed mysterious. Scientists have measured electrons from here to the far side of the galaxy. Every single one is perfectly identical. Same mass. Same charge. Same behavior. In the old billiard ball model, this was just a lucky coincidence. In the field model, it is obvious. Of course they are identical. They are all produced by the same universal field following the same set of rules. Now here is where it gets unsettling. A ripple is not a permanent thing. It can fade. It can merge with other ripples. It can transfer its energy to a different field entirely. When an electron collides with its antimatter partner, a positron, both ripples dissolve. Their energy gets converted into ripples in the photon field. Two particles vanish. Two flashes of light appear. The fields continue. The ripples end. This is what particle collisions actually are. Ripples colliding, merging, and reforming as new ripples in other fields. The particles are temporary. The fields are permanent. Physicists at the Large Hadron Collider near Geneva, Switzerland, smash protons together at speeds approaching the speed of light. When they collide, the ripples shatter and recombine into dozens of new ripples in different fields. For a tiny fraction of a second, the energy concentrated in those fields is so intense that ripples appear which normally almost never form. That is how scientists discovered rare particles, by giving fields enough energy to produce ripples they would never generate on their own. So every particle collision is really a conversation between fields. Energy flows from one field to another. Ripples form, break apart, and reform. The particles are just the readable signatures of that conversation. And the field that controls how much energy a ripple carries, how much a ripple resists being moved, leads to the single strangest discovery of the 20th century. Something invisible fills the entire universe. It slows everything down, and without it, matter as you know it could not exist. Every electron that has ever existed, every electron inside the atoms of your body, every electron inside the sun, every electron orbiting atoms in galaxies so far away that their light takes billions of years to reach us, every single one of them lives inside the same field. One field. Everywhere, always, the electron field does not start at the edge of Earth and stop somewhere in space. It does not thin out near the planets or fade between galaxies. It covers every point in the universe with equal completeness. Right now, the electron field passes through the room you are in. It passes through you. It is inside every atom of every object around you, active and present. This is one of the most mind-bending consequences of quantum field theory. Every particle type has one universal field associated with it. The electron field is one. There is a field for photons, a field for the up quark, and a separate one for the down quark. There are fields for particles so short-lived that they only appear for a fraction of a second during a high-energy collision. Each field is its own universal presence, filling all of spacetime. Now here is what makes this deeply strange. Because all electrons are ripples in the same field, they are fundamentally connected in a way that has no equivalent in everyday experience. Two electrons in the same region of space cannot occupy the same energy state. They actively push each other away from matching configurations. This rule, called the Pauli exclusion principle, is why atoms have structure. Without it, every electron in an atom would collapse into the lowest energy level, and chemistry would cease to exist. No molecules, no compounds, no biology, no you. That rule works precisely because all electrons share one field. They can feel each other's presence across the field even before they physically interact, and the field itself carries energy even when no ripples are running through it. Scientists discovered this by measuring tiny shifts in the energy levels of hydrogen atoms. The electron field in empty space fluctuates. It hums. Those fluctuations are small, but they push and pull on real electrons in measurable ways. The measurement matched the prediction to extraordinary precision. The universe is not a collection of separate particles bumping into each other by accident. It is a web of overlapping fields, each one universal, each one active, all of them woven together into a single interconnected fabric. Right now, the electron field inside your body is part of the same continuous field that stretches to the edge of the observable universe. Your electrons are not isolated particles locked inside you. They are temporary excitations of something borderless and vast. That thought sits uncomfortably with common sense. We feel separate. We feel like distinct objects moving through empty space. But the physics says the separateness is a feature of scale, not a feature of reality. At the deepest level, everything is connected through the fields it shares. So if electrons are ripples in a universal field, why do different ripples carry different amounts of mass? Why is a proton so much heavier than an electron? Why does a photon have no mass at all? The answer requires meeting the strangest field of all, one that fills the universe like a thick invisible fluid, and everything passing through it gets slowed down in a way that we experience as weight. You have been told your whole life that matter has mass, that heavy things weigh more because they contain more stuff, that a brick is heavy because it is made of dense material. That explanation feels obvious. Physics has a very different answer. Mass is a measurement of resistance. Specifically, it measures how hard it is to change the motion of an object. A ping-pong ball has low mass. You can swat it across a room with one finger. A bowling ball has high mass. The same flick barely moves it. But here is the part the textbook skips, that resistance to motion does not come from the stuff inside the object. It comes from how strongly the object's quantum fields interact with a specific invisible field that fills the entire universe. That field is the Higgs field. The Higgs field is active everywhere in the universe at all times. It does not clump, it does not flow. It simply exists at every point in space with a constant non-zero value. It never turns off. Every quantum field in the universe must interact with the Higgs field to some degree. And the strength of that interaction determines how much mass the corresponding particles carry. Think of it this way. Imagine a perfectly still swimming pool filled with thick syrup instead of water. Now drop two objects in at the same time. One is a smooth, tiny marble. It slides through the syrup easily. The other is a rough, spiked ball covered in surface texture. The syrup grabs it, drags it, slows it down. The syrup does not care how big either object is. It only cares about how much surface contact there is to grab onto. The Higgs field works the same way. The electron field interacts with the Higgs field at a certain strength, and that interaction gives electrons their relatively low mass. The quark fields interact more strongly, which is part of why protons and neutrons built from quarks are much heavier than electrons. The photon field does not interact with the Higgs field at all. That is why photons, the particles of light, have zero mass and always travel at the fastest speed allowed by physics. Massless particles must always move at the speed of light. There is no other option for them. Particles with mass always travel slower because the Higgs field constantly resists their motion. This idea sat as a theoretical proposal for almost 50 years. Scientists knew it had to be true because the math worked. But direct proof required detecting the Higgs field's own ripple, its own particle, called the Higgs boson. That particle was so rare and so short-lived that finding it required building a machine almost 17 miles around beneath the Swiss-French border to smash other particles together with enough energy to briefly excite the Higgs field into producing a detectable ripple. The moment that ripple appeared in the data was the moment humanity confirmed that mass is not a property of matter. Mass is an interaction, a relationship between a field and the invisible ocean it moves through. Your weight on a scale is not measuring how much stuff you contain, it is measuring how strongly your fields tangle with the Higgs field every moment of every day. And if the Higgs field can give particles their mass, the next question is even more strange. What fills the rest of space? What happens in the regions where no particles are present at all? The answer is that space is never truly empty, and what fills it is stranger than most people can picture. In 1964, a physicist named Peter Higgs sat down with a piece of paper and wrote out an equation that predicted something revolutionary. He proposed that the universe contains an invisible field with a property no other field had ever been given. Unlike all the other quantum fields, which sit at zero energy when undisturbed, the Higgs field sits at a non-zero value even in its lowest energy state. It is always on, always present. You cannot turn it off or remove it from a region of space. Higgs himself understood this would be the most controversial part of his proposal. A field that cannot be switched off, one that exists even in a perfect vacuum, had never been proposed before. He submitted his paper to a journal. It was rejected. The idea was too strange. He tried again. It was accepted. For nearly 50 years, the Higgs field was a prediction sitting in the math. Scientists used it because the equations only worked if it was real. Every particle's measured mass matched perfectly with the theory's predictions about how strongly that particle interacted with the Higgs field. But measuring a field directly requires finding its ripple, its boson. And producing that ripple required more energy than any machine in existence could deliver. So physicists started building. The Large Hadron Collider, constructed in a tunnel buried 300 feet beneath the French and Swiss countryside, is nearly 17 miles around. It accelerates protons to within a fraction of a percent of the speed of light and smashes them together millions of times per second. The goal was to pump enough energy into the Higgs field that it would briefly produce a detectable ripple. On July 4th of 2012, a team of thousands of scientists announced they had found it. The Higgs boson appeared in the collision data. It lasted for less than 1/60th of a second before decaying into other particles. That was long enough. The signature matched the prediction perfectly. The reaction among physicists around the world was not celebration. Several of them wept. Because this was not just the discovery of a new particle, it was experimental confirmation that mass itself is an emergent property. It confirmed that the reason your body has weight, the reason you cannot walk through walls, the reason the earth pulls you down, all traces back to an invisible field interacting with your matter every instant. And the Higgs field has another profound implication. In the very early universe, for a brief moment after the Big Bang, the Higgs field had a value of 0. Everything was massless. Every particle moved at the speed of light. There were no atoms, no stable matter, no structure of any kind. Then the Higgs field switched on. Particles slowed down. Mass appeared. Matter could now form bonds and build structure. The moment the Higgs field turned on is the moment the universe became capable of containing anything recognizable. Without it, every particle would still be screaming through space at the speed of light, unable to slow down, unable to combine, unable to build anything at all. So mass comes from the Higgs field. Light comes from a different field entirely. And the reason light has no mass, the reason it moves the way it does, is a direct result of how that field operates. What light actually is, at the field level, is one of the most elegant answers in all of physics. Light is the fastest thing in the universe. It covers about 186,000 miles every second. It takes light about 8 minutes to reach Earth from the Sun. It takes about 2.5 million years to reach us from the nearest large galaxy. None of that surprises most people. But the reason light moves so fast, and why it can never slow down to a stop, is where the real story is. Light has no mass. 0A photon, the ripple in the electromagnetic field that carries light, does not interact with the Higgs field at all. Because it has no mass, physics gives it no choice in how fast to travel. Massless particles must always move at the maximum speed the universe allows. They cannot do otherwise. The moment a photon is produced, it is already moving at full speed. The moment it is absorbed, it ceases to exist as a ripple. There is no middle state. This is not a rule someone wrote down and enforced. It falls directly out of the mathematics describing how fields propagate through space-time. A field ripple with no mass cannot be slowed. It carries energy at the universe's fundamental speed limit, and nothing can change that. Now consider what light actually is at the field level. The electromagnetic field is one of the fundamental quantum fields filling all of space-time. When a charged particle like an electron changes its energy state, it produces a disturbance in the electromagnetic field. That disturbance propagates outward as a wave. That wave is light. It does not need a medium to travel through. It is the medium, or rather, it is a ripple in a field that already fills the medium of space. This explains why light can travel through the vacuum of space with no problem. Sound needs air. Ocean waves need water. Light needs nothing except the electromagnetic field, which is everywhere. And here is something that connects this to everything else. The electromagnetic field is the same field responsible for the electric repulsion between your hand and that desk, the same field that drives every chemical reaction in your body, the same field that lets your phone screen emit visible light and receive wireless signals. The electromagnetic field is arguably the most directly experienced quantum field in everyday life, even if most people never think about it that way. Light is not a separate phenomenon that happens to move through space. Light is what the electromagnetic field does when it moves. Now, something that might seem obvious but is actually very deep. If the electromagnetic field carries light and covers all of space, and if the electron field covers all of space, and if the Higgs field covers all of space, then every point in the universe is simultaneously threaded through by dozens of overlapping quantum fields, all of them active, all of them interacting, all of them fluctuating. Even in the deepest, emptiest region of space imaginable, every one of those fields is present. And they are never perfectly still. That constant activity in seemingly empty space leads to one of the most disturbing discoveries in modern physics. One that forces scientists to completely rethink what the word empty actually means. Because the vacuum of space is not what anyone expected, and what happens inside it should be impossible. Point to the emptiest place you can imagine, a region of space billions of miles from the nearest star. No matter, no light, no signal of any kind. Cold and silent, the closest thing to pure nothing. Physics says that place is packed with activity. Every quantum field in the universe fills that region, and quantum fields cannot hold perfectly still. It is physically forbidden. The rules of quantum mechanics, specifically a principle called the Heisenberg uncertainty principle, state that you cannot simultaneously know both the exact energy of a field at a point in space and exactly how that energy is changing over time. The more precisely you pin down one value, the more wildly the other fluctuates. Perfect stillness would mean knowing both values perfectly. That is impossible. So the fields must always fluctuate. Even at their absolute lowest energy state, which physicists call the vacuum state, the fields are still oscillating constantly around that minimum. They hum. They quiver. They never fully rest. This is called the quantum vacuum, and it has real, measurable physical consequences. One of the most dramatic consequences is something called vacuum energy. The constant fluctuations of all the quantum fields in empty space add up to a background energy that fills the universe. Scientists have been trying to calculate exactly how large this energy should be. Their best theoretical estimate and their best experimental measurement disagree by a factor so enormous that many physicists call it the worst prediction in the history of physics. Getting that number right is one of the biggest unsolved problems in science today. But even without solving that big problem, the vacuum produces effects that are directly measurable in a laboratory. One of them was predicted in 1948 by a physicist named Hendrik Casimir. He proposed that if you placed two perfectly smooth metal plates extremely close together in a vacuum, the quantum vacuum fluctuations between the plates would be restricted. Only fluctuations with wavelengths short enough to fit in the narrow gap could exist there. Outside the plates, all fluctuations were free. This imbalance between the outside and the inside would generate a pressure difference, pushing the plates together with a real, measurable force. No one believed him at first. Decades later, precise experiments confirmed the effect exactly. Two plates in a vacuum, with nothing between them, pulled together by the boiling energy of the vacuum itself, empty space generating a measurable physical force. The vacuum also produces something far more dramatic: particle pairs. At any point in space, a quantum field can briefly spike in energy, producing a pair of particles, one matter and one antimatter. They appear from nothing, exist for a fraction of an instant, collide and annihilate each other. The energy is borrowed and returned so quickly that the universe's accounting balances out. Scientists call these virtual particles. You cannot catch one, you cannot see one directly. but their effect on real particles is measurable. They slightly shift the energy levels of electrons in hydrogen atoms in a way that matches the calculation precisely. Empty space is alive, and if even empty space is full of activity, the behaviour of real particles travelling through that seething vacuum produces something that sounds like a fever dream. A person moving fast enough through empty space can feel the vacuum burn. Imagine borrowing $1 from a friend, spending it instantly, and returning it so fast that neither of you can prove the transaction happened. The dollar was real for a moment. The spending was real. But no record exists, because the whole event resolved before anyone could write it down. That is how virtual particles work. The Heisenberg uncertainty principle has an energy time version. It says that the more precisely you measure the energy of a region of space over a very short interval of time, the less certain that measurement becomes. For extremely short time intervals, the uncertainty in energy is so large that the universe effectively allows a small energy debt. A field can spike in energy, produce a pair of particles, and then absorb that energy back again, as long as the whole process resolves faster than the uncertainty window closes. The particles that appear in this process are real in a specific sense. They interact. They push and pull on other particles nearby. They change the outcomes of real measurements. But they exist for such a brief moment that they can never travel to a detector on their own. They are absorbed back into the field before any instrument could register them as independent entities. This is why physicists call them virtual. They are not imaginary. They are temporary disturbances that play a real role in physics without ever becoming stable, detectable ripples, and their role is enormous. Every force between particles, every push and pull of electromagnetism, every binding grip of the strong nuclear force works through the exchange of virtual particles. When two electrons repel each other, the electromagnetic field between them is vibrating. That vibration is described mathematically as a constant exchange of virtual photons. The electrons are not throwing invisible balls at each other. The field between them is fluctuating, and that fluctuation carries the momentum that pushes them apart. Forces are fields talking to fields through virtual fluctuations. This sounds abstract, but it produces concrete results. The calculation of how an electron behaves in a magnetic field when virtual particles are included in the math matches the measured value to over 10 decimal places. Remove virtual particles from the calculation and the prediction falls apart. Their influence is real and precise, even though they themselves cannot be isolated and observed. Now, something about this should bother you. If forces are carried by virtual particles, and if virtual particles are just field fluctuations, then matter interacting with matter is really just fields interacting with fields. The particles are the symptom, the fields are the cause, and this changes the picture of forces completely. Gravity pulls you toward Earth, magnetism draws iron to a magnet, your muscle contractions move your arm. At the quantum level, every one of these is a field disturbance propagating through space, carrying information and momentum from one set of field ripples to another. Virtual particles make the invisible machinery of forces visible, at least in the math. But forces are only half the story, because those same fields that generate virtual particles also determine where a real, stable particle can be found. And the answer to that question breaks every intuition you have about what objects are. A particle does not have a location. It has a cloud of possible locations. And choosing to look for it changes where it ends up. In a laboratory in the Netherlands in the 1990s, a team of physicists placed two flat metal plates facing each other in a vacuum. The gap between them was smaller than the width of a human hair. There was nothing between those plates. No gas, no light, no particles of any kind. Just empty space. The plates moved toward each other. Nothing pushed them, nothing pulled them in the conventional sense. There was no magnet, no static charge, no wire connected to either plate. The experimenters had done everything possible to eliminate every known force. And still, the plates were drawn together with a measurable, predictable force. They confirmed what Hendrik Casimir had calculated decades earlier. The vacuum of space, that completely empty gap between the plates, was generating a real physical force. Here is how. The quantum vacuum is full of fluctuating energy. Every quantum field fills that gap between the plates, and every field is constantly producing tiny energy spikes of all different sizes. These spikes occur at all different wavelengths, some are short and some are long. In the open space outside the plates, all wavelengths are free to exist. Between the plates, only wavelengths short enough to fit in the narrow gap can exist. The long wavelengths are simply too large to form in that confined space. This creates an imbalance. Outside the plates, the vacuum pushes with contributions from every wavelength. Inside the gap, only the short wavelengths contribute. The outside pressure is slightly larger. The plates get pushed together by the difference. The force is tiny. To feel it with your hand, you would need plates the size of a dinner table separated by less than the diameter of a red blood cell. But it is measurable with precise instruments, and every measurement has confirmed the prediction exactly. This matters beyond the laboratory result itself. The Casimir effect is direct physical proof that the quantum vacuum is not passive. Empty space exerts force. The nothingness between those plates is not doing nothing. It is vibrating with every frequency the laws of physics allow, and that vibration has consequences that reach out and move real objects. Some engineers have even begun exploring whether the Casimir effect could be useful. At scales where machine parts are separated by nanometer gaps, vacuum pressure becomes a real engineering consideration. The quantum vacuum is not an abstract curiosity at that size. It is a practical force to account for. The Casimir effect also provides indirect evidence for something even stranger. If the vacuum between two plates is doing this, then the vacuum everywhere is doing the same thing. The universe is not sitting in empty, neutral space. It is sitting in a churning sea of quantum energy that presses on everything from every direction simultaneously. The vacuum is not the absence of the universe, it is the baseline state of the universe. And the baseline state is active, energetic, and never fully calm. Now, if empty space already does this much, what happens when you try to catch a single particle inside it? When you try to pin down exactly where one electron is and measure it precisely? The answer is one of the most disturbing experiments ever performed, and it revealed that the act of looking changes reality itself. A ball rolled at a hill either makes it over or rolls back down. Every person who has ever thrown anything understands this. You need enough energy to clear an obstacle. If you fall short, you stop. This rule feels permanent and obvious. Quantum fields ignore it completely. An electron approaching a barrier it does not have enough energy to cross will sometimes appear on the other side anyway, not by going over or around, by passing through. This is called quantum tunneling, and it is real, measurable, and it powers the device you are using to listen to this right now. Here is how it works at the field level. An electron is a ripple in the electron field. That ripple does not have a single hard location. It has a shape that spreads out across space in a wave pattern. The wave extends into the region of the barrier. Inside the barrier, the amplitude of the wave drops rapidly. For most barriers, it drops to zero before the other side. But if the barrier is thin enough, the wave still has a measurable amplitude on the far side. That amplitude represents a real probability that the electron will be found there. When the electron is detected, it collapses from that spread out wave into a specific location. Sometimes that location is on the other side of the barrier, even though the electron never had enough energy to travel through the barrier classically. The wave nature of the field ripple allowed it to reach both sides simultaneously. The barrier was penetrated without the electron ever being inside it. Every transistor in every modern computer chip depends on this. Electrons tunnel through thin insulating layers billions of times per second as part of normal operation. Remove quantum tunneling and modern electronics stops working immediately. The computers that run hospitals, power grids, financial systems, and communication networks all function because electrons pass through solid barriers they have no classical right to cross. Quantum tunneling also powers the sun. The core of the sun is not actually hot enough, by classical physics standards, to force hydrogen nuclei close enough together to fuse. The repulsion between positively charged protons should prevent fusion at solar core temperatures. But protons are also quantum field ripples. Their wave functions overlap even when their classical energies say they should be too far apart. Tunneling allows fusion to proceed. Without it, the sun goes dark, the Earth freezes, life ends. So quantum tunneling is not an exotic edge case. It is the reason the sun shines, and the reason your phone works. It is woven into the basic physics of the universe, and it reveals something profound about solid barriers. A wall is a region of space where the quantum fields interact in ways that prevent classical particles from passing. But a field ripple is not a classical particle. It extends beyond its apparent position. It leaks into regions that seem forbidden. It can, under the right conditions, appear where common sense says it cannot be. Solid is a word that describes experience, not physics. At the field level, barriers are probabilities, and probabilities have tails that extend into the forbidden zone. If tunneling already bends reality this far, the next experiment bends it further. Because an electron approaching two openings at once reveals that particles do not travel paths at all, they travel something far stranger. Fire a single electron at a wall with two narrow slits in it. On the other side, a detector screen records where the electron lands. You would expect one of two things. Either the electron goes through the left slit or the right slit and lands somewhere on the screen consistent with one of those two paths. That is how baseballs work. That is how any classical object works. The electron does something else entirely. When the electron reaches the screen, it lands in a pattern that can only be produced by a wave passing through both slits simultaneously and interfering with itself. The bright and dark bands on the detector screen, called an interference pattern, are the signature of two waves meeting and either adding together or cancelling each other out. A single particle, sent through one at a time, builds this pattern over thousands of repeated shots. Each electron, by itself, passes through both slits. As a wave. As a spread-out ripple in the electron field. The ripple encounters both openings, divides, passes through both, and the two halves of the wave meet on the other side and interfere. Only when the wave hits the screen does it collapse into a single detection point. Now here is the part that made physicists lose sleep for decades. If you place a detector near one of the slits to check which path the electron took, the interference pattern vanishes. Instantly, every electron now lands in one of two simple clusters, exactly where a classical particle would land. The wave behavior disappears the moment you try to observe it. The electron somehow knows it is being watched. This is not a metaphor. Every experiment designed to extract which path information eliminates the wave pattern. The more information you gain about the path, the more the wave behavior disappears. The electron trades wave-like spread for particle-like precision based on whether path information is recorded in the universe, even if no human ever reads that record. The explanation from quantum field theory is precise. The electron is a ripple in a field. A ripple naturally spreads. When a detector interacts with the field near one slit, it entangles with the electron's field state. This entanglement collapses the spread of the ripple into a more localized form. The wave behavior requires the ripple to be spread across both paths. Entanglement with a detector destroys that spread. The act of measuring is a physical interaction between fields, and that interaction has real consequences for the quantum state. This experiment has been run with single electrons, single photons, single atoms, and even with molecules containing 60 carbon atoms arranged in a soccer ball shape. Every time, the same result. Wave behavior unless observed. Particle-like behavior the moment path information enters the universe. The quantum world does not hide its wave nature out of shyness. The wave nature is what it is. The particle nature is what happens when the wave gets entangled with the measuring world. And if a particle's wave nature can be destroyed by measurement, then what exactly is a particle's position when no one is looking? The answer is that it does not have one. And the mathematics of that answer is one of the strangest structures in all of science. A quantum field ripple, left on its own, spreads. It follows a mathematical rule called the Schrödinger equation. This equation tells you how the wave evolves over time. The wave can be in many states simultaneously. An electron's wave function can describe a particle that is, in a real mathematical sense, in multiple locations at once, with each location having a certain probability of being the one where the electron appears. This is called a superposition, and it is the normal state of a quantum system. Then something interacts with it. An atom in a detector, a photon hitting a screen, a molecule in your eye. The moment the quantum field ripple entangles with the detecting system, the spread of possibilities snaps into a single outcome. One location, one measurement, one result. This snapping is called wave function collapse, and it is one of the most argued about ideas in physics. Here is what makes it so uncomfortable. Before measurement, the electron does not have a hidden secret location that we just do not know. The mathematics is clear. The spread of possibilities is the real description of the electron's state. The electron is genuinely in multiple states at once. After measurement, it is in one state. The collapse is a physical change in the field's configuration, triggered by interaction with the measuring environment. This means the universe does not have a definite classical state independent of observation. The state that gets recorded depends on which measurement happens, and different measurements of the same system can yield outcomes that cannot both have been simultaneously true beforehand. Albert Einstein spent decades arguing this could not be right. He believed there had to be hidden variables, definite properties the electron carried all along, which measurement merely revealed. Experiments performed decades after his death, based on work by physicist John Bell, proved Einstein wrong. The spread of outcomes before measurement is real. The electron genuinely did not have a single definite location. The universe keeps its options open until interaction forces a choice. Physicists have confirmed this with increasingly creative experiments. They have delayed the decision of which measurement to make until after the particle was already detected, changing the experimental setup after the fact. The results shifted to match whichever measurement was ultimately chosen, even though the particle had already arrived. The timeline of cause and effect seemed to bend. This is not a flaw in the measurement apparatus. This is how quantum fields work. Now here is what this means for the field picture. When a particle has no definite position, it is because the field ripple is genuinely spread. The field is in a superposition of configurations. The ripple simultaneously has contributions from multiple regions of space. No single location is more real than any other until the field interacts with something that forces it to commit. And every measurement in your life is this interaction happening. Your eyes, your ears, your nervous system are all made of atoms, which are fields which are constantly interacting with the world around them, constantly collapsing quantum possibilities into the specific classical experience you call reality. You are a measuring device made of the things being measured. But even within that classical experience, the quantum world keeps sending hints that something stranger is happening beneath the surface. Because the field ripple you call an electron has a shape, and that shape has no hard edge, no boundary, no outer wall. What that means for the idea of a particle as a thing will make the old model feel permanently broken. Draw a circle on a piece of paper. That circle has a clear boundary. Inside is inside. Outside is outside. For centuries, scientists pictured atoms as having the same kind of definite boundary, a hard-edged electron orbiting a hard-edged nucleus like a tiny moon around a tiny planet. That picture is gone. An electron does not have an edge. it has a probability distribution. Mathematically, the electron's wave function extends across all of space infinitely. The probability of finding it very far from where you expect drops rapidly. But it never reaches exactly zero. The electron's influence, its field ripple, technically extends to the edge of the universe. In practice, the probability outside of a very small region around the atom is so tiny it is unmeasurable. But the principle matters enormously. There is no hard wall where the electron ends. There is only a gradient from highly probable to deeply improbable. The electron fades rather than stops. This is why quantum tunneling happens. The wave function does not vanish at the wall. It decays through the wall and sometimes has enough amplitude on the other side to allow detection there. If the electron had a hard edge, tunneling would be impossible. The fuzzy, spreading nature of the field ripple is exactly what makes tunneling work. Now apply this to atoms. An atom's boundary is not a hard shell. It is the region where the electron's probability cloud is most dense. Two atoms bonding together is two probability clouds overlapping and reshaping each other into a combined configuration that is energetically stable. A chemical bond is two field ripples merging into a new joint pattern. Every molecule in your body is a web of overlapping, fuzzy, edgeless probability clouds. Every protein, every strand of your DNA, every cell membrane is a complex network of electron field ripples interlocked by shared probability gradients. There are no hard connections anywhere in the structure of matter, only smooth, continuous field interactions. A mathematician named Hegefeld proved something even more striking. He showed rigorously that if you try to define a particle as something strictly confined to a finite region of space, a particle with a true hard edge, you immediately get a contradiction with the rules of relativity. A strictly localized particle would violate the speed limit of the universe. The mathematics forces the conclusion strictly localized particles cannot exist. The fuzziness is mandatory. This proof, called the Hegefeld theorem, is one of the strongest mathematical arguments that particles as hard, bounded objects are simply incompatible with the laws of physics. Fields with spread-out ripples are the only description that survives, so the solid, hard, bounded particle is ruled out by the math itself. But if no particle has a hard edge, and if every particle is a spread-out ripple in a universal field, then the separation between two distant particles is less absolute than it appears. Two ripples in the same field can be connected in ways that cross any distance, and that connection, confirmed in laboratories around the world, produces an effect that Einstein called spooky. An effect that makes instant communication across the universe seem almost plausible. Almost, two particles on opposite sides of the room share a measurement. Measure the spin of one, and the other instantly shows the opposite spin, regardless of distance. No signal passes between them. No force connects them. The result is simply correlated, perfectly and instantly, across any gap. Albert Einstein called this spooky action at a distance. He found it deeply troubling and spent years trying to explain it away. Every attempt failed. Experiments have now confirmed it works across distances of over 1,000 miles. The correlation is real. And it makes complete sense once you see particles as ripples in a shared field. When two particles become entangled, it means their field ripples have combined into a single joint configuration. They are no longer two separate ripples. They are one ripple with two measurement outcomes spread across it. That joint configuration exists across whatever distance separates the particles. The field itself carries the correlation. When you measure one particle, you interact with one part of the joint field ripple. That interaction collapses the joint configuration everywhere simultaneously. The other particle, as part of the same configuration, instantly reflects the collapse. The distance is irrelevant because the connection is in the field, and the field is everywhere. This does not allow you to send information faster than light. The result of your measurement is random. You cannot choose which outcome you get, so you cannot control what the distant particle shows. You can only compare notes with the person at the other end after the fact, which requires ordinary slower than light communication. The spooky correlation is real, but it carries no message you can control. What it does reveal is that two particles that have ever interacted share a piece of the same field configuration. They are parts of a single quantum object spread across space. Separating them physically does not separate them in field terms. Now scale this up. Every particle in the early universe was packed into a region smaller than an atom. Everything interacted with everything else. Over billions of years, those particles spread across the universe in every direction. But the entanglements formed in that early compressed state were never fully erased. The universe carries an enormous web of quantum correlations woven through every field, connecting particles across cosmic distances, reflecting interactions that happened when the universe was younger than a single heartbeat. You are entangled with the universe. Every atom in your body was forged inside a star and ejected in an explosion. Those atoms interacted with other atoms across billions of years of cosmic history. The field states of every particle carry traces of those ancient interactions. The universe is not a collection of isolated objects. It is a continuous, interconnected field configuration that has been evolving since the Big Bang. Every measurement you make, every photon your eyes absorb, every chemical reaction in your brain is a local interaction within a vast entangled web. And the map of every field in this web, every known force and particle accounted for in a single mathematical framework, is one of the greatest achievements in the history of human thought. It is called the Standard Model, and it covers almost everything. Almost. Physicists spent most of the 20th century doing something no generation had attempted before. They mapped the invisible. Every time a new particle appeared in a detector, every time a force was measured with a new level of precision, every time a collision produced an unexpected result, scientists asked the same question: what field is responsible for this? Over decades of experiments, conferences, competing theories, and breakthroughs that arrived in the middle of the night, a picture emerged. The Standard Model is that picture. It is a complete mathematical description of every known fundamental field in the universe and how they interact with each other. It accounts for 12 matter fields. 6 of them are quark fields, producing the particles that build protons and neutrons. The other 6 are lepton fields, producing particles like the electron, the muon, and the 3 types of neutrino. Each field generates particles with specific masses, charges, and behaviors, all determined by how strongly that field couples with the others. On top of the matter fields, the Standard Model describes the force-carrying fields. The electromagnetic field carries the photon. The strong nuclear force field carries particles called gluons, which bind quarks together inside protons and neutrons. The weak nuclear force field carries particles called W and Z bosons, which allow certain particles to change identity and power the nuclear reactions inside the Sun. And sitting above all the matter fields, coupling to most of them and giving them their mass, sits the Higgs field. Every stable atom, every chemical element, every molecule, every cell in every living organism traces its structure back to the interactions of these fields. The entire physical world you experience is built from the outputs of this set of equations. The Standard Model has been tested more thoroughly than any other theory in science. Its predictions for the magnetic behavior of the electron match measured values to a precision equivalent to measuring the distance from New York to Los Angeles and being off by less than the thickness of a human hair. No other scientific framework in history has achieved this level of verified accuracy. Scientists working at the Large Hadron Collider have spent decades searching for cracks in the Standard Model, for results that it cannot explain, for particles it did not predict. Most searches have come up empty. The Standard Model keeps winning. And yet physicists know it is incomplete. The Standard Model has no field for gravity. Every force in everyday experience except gravity has a quantum field and a corresponding particle. Gravity remains outside the framework, described only by Einstein's general theory of relativity, which treats it as a curvature of space-time rather than a field ripple. The two descriptions work beautifully in their own domains. When you try to combine them mathematically, the equations produce nonsense. The Standard Model also has nothing to say about dark matter. Roughly 85% of the matter in the universe does not interact with the electromagnetic field at all. It produces gravity, but emits no light. No field in the Standard Model accounts for it. So the most precisely tested theory in science still leaves the majority of the universe unexplained. The next fields humanity needs to find, the ones that carry gravity and generate dark matter, may require experiments beyond anything built so far. Or they may require entirely new mathematics. Or they may require letting go of assumptions so deep that no one has yet questioned them. And the biggest missing piece of all, the force that shapes every galaxy and governs the fate of the universe, still has no quantum field to its name. What gravity actually is, at the field level, is the question that could break everything we thought we knew. Inside every atom, something impossible is happening. The nucleus at the centre of every atom contains protons packed together in an extraordinarily tight space. Protons carry positive electric charge. Positive charges repel each other with tremendous force. The closer they get, the harder they push apart. Inside a nucleus, they are separated by distances so tiny that the repulsion should be catastrophic. Every nucleus in the universe should explode the instant it forms. Every atom should be impossible. And yet here we are. Something holds the nucleus together against that repulsion. Something so powerful that it overwhelms the electromagnetic force completely at short range. Scientists call it the strong nuclear force, and it is roughly 100 times more powerful than electromagnetism at the distances inside a nucleus. The strong force operates through its own quantum field. The ripples in that field are called gluons. Gluons are the particles exchanged between quarks, the even smaller pieces that make up protons and neutrons. But gluons behave completely differently from photons in the electromagnetic field. Photons get weaker as they travel farther. The electromagnetic force fades with distance. Gluons do the opposite. The strong force gets stronger as quarks try to pull apart. Imagine trying to stretch a rubber band between two quarks. The further apart they get, the harder the band pulls them back. If you stretch far enough, the band does not snap. Instead, the energy stored in the stretched field becomes large enough to produce a new pair of quarks. You pull one quark away and instead of freeing it, you create two new quarks from the field energy. The original quark remains bound. You end up with more particles than you started with. This is why quarks are never found alone in nature. Pull one out of a proton, and the strong field immediately creates partners to recapture it. Physicists call this quark confinement. Every attempt to isolate a single quark ends with a new bound pair forming from the energy of the attempt. Inside the proton, three quarks are bound by a constant exchange of gluons. But here is something deeply strange. The combined mass of those three quarks accounts for only about 1% of the proton's total mass. The remaining 99% comes from the energy of the gluon field binding them together. The proton is almost entirely made of field energy. The quarks are tiny ripples. The binding energy is the substance. This means that almost all of the mass of ordinary matter, the mass of every proton and neutron in every atom in your body, comes not from particles, but from the energy stored in the strong force field. Your mass is field energy. Your body is held together by the most powerful force in the universe, operating inside every atom of your flesh, every moment, without pause. The sun generates energy by forcing protons close enough for the strong force to grab them and fuse them. The energy released in that fusion is the energy given off when the strong force pulls protons into a more stable configuration. Sunlight is the strong force field releasing excess binding energy. Every warm day, every plant that grows, every ocean current that moves is powered ultimately by the strong force field vibrating inside the sun. And while the strong force binds the nucleus together Another field governs a completely different kind of transformation happening inside that same nucleus. One that changes the identity of particles entirely and makes the sun burn steadily over billions of years. The strong force grips quarks and never lets go. The electromagnetic force pushes and pulls charged particles. But neither of those forces can change what a particle fundamentally is. The weak nuclear force can. The weak force field carries particles called W and Z bosons. These are the heaviest force-carrying particles in the Standard Model, roughly 80 to 90 times heavier than a proton. Their enormous mass is why the weak force operates only at extremely short range, far shorter than the diameter of a proton. But within that tiny range, it does something no other force can do. It transforms one type of quark into another, changing the identity of the particle it acts on. Inside the Sun, hydrogen nuclei need to fuse together to release energy. But two protons carry the same positive charge and repel each other fiercely. For the Sun to burn steadily over billions of years rather than exploding in a single catastrophic burst, the fusion process needs to be slow and controlled. The weak force is responsible for that control. When two protons fuse, one of them must transform. The weak force converts one of the up quarks inside a proton into a down quark. This changes the proton into a neutron. A neutron carries no electric charge and bonds easily with the remaining proton to form a stable nucleus called deuterium. This process happens at a slow rate governed entirely by how infrequently the weak force acts. The Sun has been burning for about 4.5 billion years and has enough hydrogen to burn for another 5 billion because the weak force keeps the fusion rate manageable. Remove the weak force and the Sun either goes cold or explodes. Either way, Earth becomes uninhabitable within seconds. The weak force is also responsible for a process called beta decay. Inside unstable atomic nuclei, a neutron can spontaneously convert into a proton by transforming one of its down quarks into an up quark. This transformation releases an electron and a nearly massless particle called a neutrino. This decay process is what makes certain elements radioactive. It is also the process that generates the heat deep inside Earth from the decay of radioactive elements in the planet's mantle. That internal heat drives plate tectonics. Without beta decay, the continents would not move. The geological cycles that regulate Earth's carbon and oxygen levels would shut down. Radioactive decay makes the ground under your feet warm. It moves the continents. It keeps the oceans chemically balanced for life. The weak force also breaks a fundamental symmetry that every other force in nature obeys. Most physical processes work identically whether you run them forward or backward in time, or whether you view them in a mirror. The weak force does not. It has a preference for left-handedness that no other force shares. Scientists discovered this in 1956, when an experiment showed that the direction of electron emission during beta decay depended on which way a magnetic field was oriented. The universe, at the level of the weak force field, has a preferred direction. Why the weak force breaks this symmetry while no other force does is one of the deepest unsolved puzzles in particle physics. The weak force quietly governs radioactivity, stellar burning, Earth's internal heat, and a fundamental asymmetry of the universe. All of it through one field and two incredibly massive ripples in that field. But the force that shapes your daily experience most directly is neither the strong nor the weak force. It is the field you interact with every moment of your waking life. Right now, light from the room around you is hitting your eyes. Every nerve signal firing in your brain is moving through electrical charge. Every chemical bond in your body is held together by shared electrons. Every screen, every speaker, every motor, every signal travelling through the air to your phone operates through the same force. The electromagnetic field governs all of it. The electromagnetic force is carried by photons, the ripples in the electromagnetic field. It acts on anything with electric charge. Electrons carry negative charge. Protons carry positive charge. Opposite charges attract. Like charges repel. This simple rule operating through the constant exchange of virtual photons across the electromagnetic field, produces the entire structure of chemistry. Every atom holds together because the negatively charged electrons are attracted to the positively charged nucleus. Every chemical bond between atoms forms because electrons find shared configurations between two nuclei that lower their total energy. Every protein folds into its three-dimensional shape because the electromagnetic forces between its atoms pull it into the most stable arrangement. Every enzyme in your body functions because its shape is maintained by electromagnetic field interactions. Your body is an electromagnetic machine operating through quantum fields. The strength of the electromagnetic force at atomic scales is roughly 10,000 trillion times stronger than gravity. Gravity dominates at the scale of planets and galaxies because it acts on mass, and mass accumulates enormously at large scales. But at the scale of atoms, gravity is completely negligible. Chemistry is purely electromagnetic. The electromagnetic field also operates across vast distances. Light from galaxies billions of light years away reaches your eye because the electromagnetic field carries those photons across the universe without loss. The field never ends. The photons travel until they interact with something. A distant galaxy emitting light 4 billion years ago sends that light outward in every direction. And some of those photons, crossing billions of light years of space, end their journey by hitting the retina of a human eye and producing the experience of seeing a faint star. Every visible object in the universe is visible because of the electromagnetic field. Radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays are all electromagnetic waves. They are ripples in the same field, differing only in their frequency and the energy they carry. The range of frequencies in the electromagnetic field spans a factor of more than 1 trillion from the lowest radio waves to the highest energy gamma rays. Visible light, the narrow band your eyes detect, occupies less than 1% of that range. You are swimming in electromagnetic radiation at every moment. Radio signals from hundreds of stations pass through your body right now. Infrared heat radiates from every surface around you. The electromagnetic field fills your room, your city, your planet, and every corner of the universe beyond. And the same equations that describe radio waves crashing through the air also describe the forces holding your DNA together. James Clerk Maxwell wrote down those equations in the 1860s. When physicists merged them with quantum mechanics a century later, the result was quantum electrodynamics, the most accurate theory ever tested. A field described before anyone understood atoms now explains all of chemistry, all of light, and all of technology. But the electromagnetic field can do something even stranger than carry light or hold atoms together. It can map the inside of a living body in extraordinary detail without cutting it open by disturbing the quantum fields inside your own cells. You lie inside a large white tube. A magnetic field 100,000 times stronger than Earth's natural field switches on around you. Then precise pulses of radio waves fire through your body. A few minutes later, a computer produces a detailed three-dimensional image of every tissue, organ, and blood vessel inside you, without a single incision, without any radiation that damages cells. Magnetic resonance imaging works because quantum fields inside your body respond to external fields in a predictable way. Here is the physics. Your body is roughly 60% water. Every water molecule contains 2 hydrogen atoms. Each hydrogen nucleus is a single proton. Protons have a quantum property called spin, which makes them behave like tiny magnets. Under normal conditions, the spins of the protons in your body point in random directions and cancel each other out. When you enter the strong magnetic field of the scanner, something changes. The protons align with the field, like compass needles snapping toward north. They do not align perfectly. They wobble slightly around the field direction, rotating at a specific frequency determined by the strength of the magnetic field and the quantum properties of the proton. This wobble is called precession. Now the radio wave pulses arrive. They are tuned to exactly the precession frequency of the protons. This is the key detail. The radio waves match the quantum resonance of the proton's spin field so precisely that they knock the protons out of alignment. The protons absorb energy from the radio field. When the pulses stop, the protons relax back toward alignment and release that absorbed energy as a faint radio signal. The scanner detects those faint signals and measures how long each region of tissue takes to relax. Different tissues, fat, muscle, bone, fluid, all have different relaxation times because the water molecules in them are in different chemical environments. The field interactions differ slightly depending on the molecular neighbourhood. The computer translates those timing differences into contrast in the final image. The entire process is a conversation between the scanner's external electromagnetic field and the quantum spin fields of protons inside your body. No dye needed, no radiation that breaks chemical bonds, no contact with the tissue at all, just field talking to field. An MRI can distinguish between a healthy brain and one with a tumour. It can show a torn ligament in a knee. It can map blood flow in real time. It can detect early signs of stroke minutes after they begin. All of this diagnostic power comes from measuring tiny quantum field effects inside water molecules. Medicine changed permanently the moment physicists understood how quantum fields inside living tissue responded to external fields. A discovery made in university physics labs, driven by fundamental curiosity about how proton spins work, became the tool that saves millions of lives annually. This happens repeatedly in the history of science. Understanding fields at the deepest level always produces applications that the original researchers never imagined. But fields also reveal truths that no application can soften. Truths about the nature of the particles that fields produce. Because a team of mathematicians proved something that should have ended the billiard ball model of particles once and for all. They proved, with pure logic, that hard-edged particles cannot exist in a universe governed by both quantum mechanics and relativity. The proof is airtight, and most people have never heard of it. In the 1970s, a mathematician and physicist named Gerhard Hegefeld sat down to examine a simple question. If you could somehow prepare a particle in a perfectly localized state, confined to a specific finite region of space with zero probability of being found outside that region, what would happen next? The answer he derived broke the model of particles as bounded objects. Hegefeld used only two assumptions. First, the rules of quantum mechanics govern how states evolve. Second, the universe obeys special relativity, meaning no influence can travel faster than light. Both assumptions are among the most thoroughly confirmed in all of physics. Neither is controversial. From those two assumptions alone, he proved that a particle in a perfectly localized state would instantly develop a non-zero probability of being found arbitrarily far away. The wave function would spread to infinite distances in zero time. Instantly, a strictly bounded particle, one with a hard edge and zero presence outside a finite region, is mathematically required to violate the speed of light the instant after it is prepared. A particle with a true hard edge cannot exist in a universe with a speed limit. The escape from this contradiction is the same escape quantum field theory already provides. Particles are field ripples. Field ripples naturally spread. They never have hard edges. Their wave functions extend to infinity with exponentially decreasing probability. The spread is not a problem. It is the correct description. The Hegefeld result is a mathematical proof that this field picture is not optional. Hard-edged particles produce logical contradictions. Spread-out field ripples do not. This matters because it closes a loophole that critics of quantum field theory sometimes reach for. The argument that particles are probably real solid objects and the wave-like behaviour is just a mathematical convenience is ruled out by Hegefeld. The wave-like, spread-out, fuzzy nature of particles is not a limitation of our description. It is a mandatory feature of any description compatible with both quantum mechanics and relativity. You cannot have bounded particles in this universe. The math says so. For most people, this theorem is invisible. It does not appear in high school or introductory university physics. It sits in specialized literature. But its implication is one of the most forceful in all of fundamental physics. Every particle you have ever imagined as a tiny hard ball is a category error. The ball picture was always wrong, and Hagefeld proved it has to be. What survives as the correct picture is a field, continuous, unbounded, spread across all of space, producing ripples that carry the properties we call particle properties, with probability gradients that fade but never fully reach zero anywhere in the universe. The solid object is a story we told to make the math easier to picture. The field is what the math actually describes. And fields produce forces. Every push and pull in the universe, every attraction, every repulsion, every bond, every decay, traces back to one field interacting with another. Understanding exactly how that works means understanding all four forces of nature from a single framework. 3 of those forces fit cleanly into that framework. The 4th one refuses. And its refusal points toward the deepest unsolved problem in physics. For most of history, forces seemed to be different things. Gravity pulled objects toward each other. Magnetism drew iron to lodestones. Electric sparks jumped between charged objects. Nuclear reactions released energy from atoms. Each seemed like a separate phenomenon requiring separate explanations. Quantum field theory revealed that all forces work through the same underlying mechanism. One field excites another. The disturbance carries energy and momentum from one region to another. That transfer of energy and momentum is what we experience and measure as a force. The electromagnetic force works this way. An electron sits in the electromagnetic field and distorts it by its presence. Another charged particle nearby feels that distortion and responds. Physicists describe this interaction as an exchange of virtual photons. The electron field and the electromagnetic field are constantly coupled. Every charged particle is permanently tied to the electromagnetic field, constantly disturbing it and being disturbed by it. The strong nuclear force works the same way. Quarks sit in the strong force field and exchange virtual gluons constantly. Those exchanges bind quarks together inside protons and neutrons. The gluon field is so energetic inside a proton that the binding energy of the gluons contributes more mass to the proton than the quarks themselves do. The force field becomes part of the matter. The weak nuclear force operates through the exchange of the massive W and Z bosons. Because these force-carrying particles are so heavy, the weak force has a very short range. The field disturbance decays quickly. But within that short range, the weak force can do what no other force can: transform one type of field ripple into another. All 3 of these forces fit inside a single mathematical framework. Scientists combined the electromagnetic and weak forces into a unified description in the 1960s and 70s. The combined theory predicted the W and Z bosons before they were discovered. When experiments found them exactly where the theory said they would be, it confirmed that 2 seemingly different forces were aspects of one underlying field structure. Attempts to merge the strong force into that same framework have had partial success. The mathematics suggests all 3 forces might unify at energies far beyond anything achievable in current accelerators. At those energies, the 3 distinct force fields might dissolve into a single unified field. This idea is called grand unification. It remains a prediction without direct experimental confirmation. But the track record of unification in physics is excellent. Every time 2 forces that seemed different turned out to share a deeper structure, the unified description was more powerful and more predictive than the separate ones. Gravity has not joined this story. Gravity is described by general relativity as the curvature of space-time caused by mass and energy. When physicists try to build a quantum field theory of gravity and describe it through force-carrying particles called gravitons, the math produces infinities that cannot be resolved. The equations break. The calculation gives nonsense answers for any process involving very high energies. 3 forces fit beautifully into the field framework. One refuses to enter, and that refusal is not a minor technical problem to be cleaned up eventually. It is a sign that something fundamental is missing from our picture of reality. The theory that should unify everything stops working the moment gravity joins the room. The field that should carry gravity has never been detected. The particle that should ripple through it has never appeared in any experiment. And finding it may require ideas that no one has written down yet. Every force in the standard model has a quantum field with a corresponding particle. The electromagnetic force has the photon, the strong force has the gluon, the weak force has the W and Z bosons. Each of these was predicted mathematically before it was found in experiments. Each confirmation strengthened confidence in the field framework. Gravity has no confirmed quantum field, no confirmed particle. This is the largest gap in fundamental physics, and it has remained unfilled for nearly a century. The problem is not that scientists have not tried. Physicists have spent decades attempting to build a quantum theory of gravity using the same tools that worked for every other force. The attempt always ends the same way. When you calculate the probability of a gravitational interaction using quantum field methods, the answer comes out as infinity. Infinite probabilities are physically meaningless. Something is wrong with the approach. In general relativity, Einstein described gravity as the curvature of spacetime itself. Mass and energy warp the fabric of spacetime, and other objects move along the curves produced by that warping. This picture works extraordinarily well at large scales. The orbits of planets, the bending of light around the sun, the behavior of black holes, the expansion of the universe, all of it matches general relativity's predictions with extraordinary precision. But general relativity treats spacetime as a smooth, continuous backdrop. Quantum mechanics treats everything as discrete, probabilistic, and fundamentally granular at the smallest scales. Combining a smooth, continuous spacetime with a granular, probabilistic quantum framework produces mathematical contradictions that nobody has resolved. The two greatest theories in physics are mutually incompatible. They work in their own domains. General relativity governs stars, galaxies, and the large-scale structure of the universe. Quantum field theory governs atoms, particles, and the forces between them. In everyday physics, both work perfectly, because the scales at which they conflict are so extreme that the contradiction never shows up in practice. But at the centre of a black hole, or at the moment of the Big Bang, both theories must apply simultaneously. In those extreme conditions, the contradiction cannot be ignored. Both theories predict different things, both cannot be right, and nobody knows which framework needs to change, or whether both need to be replaced by something entirely new. Theorists have proposed candidate theories. String theory suggests that the fundamental objects are not point-like field ripples, but tiny vibrating filaments, whose different vibration patterns produce different particles. One of those vibration patterns would correspond to the graviton. Loop quantum gravity proposes that spacetime itself is not continuous, but made of discrete chunks, like pixels in a photograph. Both approaches have produced interesting mathematics. Neither has produced a testable prediction that experiments have confirmed. The graviton, the hypothetical ripple in a gravitational field, may exist, but detecting it would require an instrument so sensitive that building one would be physically impossible with any conceivable technology. A graviton carries so little energy that a detector the size of Jupiter would need to run for longer than the current age of the universe to have a reasonable chance of registering a single event. Gravity sits at the centre of everything and remains the most mysterious of all forces, and the universe has arranged things so that finding its field particle may be permanently beyond reach. But gravity is not the only mystery the standard model leaves unexplained. Most of the universe is made of something that produces gravity, but appears in no field anyone has ever identified. If gravity is a force, and if every force in the universe operates through a quantum field with a corresponding particle, then there should be a particle for gravity. Physicists call this hypothetical particle the graviton. On paper, the graviton's properties are straightforward to derive. It must be massless, like the photon, because gravity acts across infinite distances and massless particles can travel indefinitely without decay. It must carry 2 units of quantum spin, twice the spin of a photon, because the mathematics of how a spin 2 particle interacts with matter reproduces the predictions of general relativity at low energies. Every other property follows cleanly from the requirement that the graviton's field must reproduce Einstein's equations in the appropriate limit. The theory is internally consistent. The problem is not the theory, the problem is the energy scale. Gravity is incomparably weaker than every other force. The electromagnetic force between an electron and a proton is roughly 10,000 trillion times stronger than the gravitational force between them. This is not a rounding error. This is an almost incomprehensible difference in strength. And because gravitational interactions are so weak, gravitons carry extraordinarily little energy. Detecting a single graviton would require a device sensitive enough to register energy differences far smaller than any instrument ever built. Physicist Freeman Dyson calculated the requirements and concluded that a graviton detector built from any material would need to be so massive that it would collapse into a black hole under its own gravity before it could detect anything. The physics itself prevents the experiment. This places the graviton in a strange category. Most particles were predicted and then detected within decades. The Higgs boson took 48 years from prediction to detection, which felt like an eternity. The graviton has been on the theoretical books for roughly as long, and has no plausible path to experimental confirmation. Some physicists have proposed indirect methods. Gravitational waves, ripples in space-time itself produced by massive collisions like merging black holes or neutron stars, were detected in 2015 using instruments called LIGO, which measured changes in distance smaller than 1/10,000th the diameter of a proton. Gravitational waves are a classical phenomenon, not a quantum one. Finding them did not confirm gravitons, but if gravitational waves exist at the classical level, and if quantum mechanics applies to everything, then gravitons should exist as the quantum version of those waves. That argument is compelling, but indirect. The situation points to something deeply uncomfortable. Physics has always advanced by detecting what theory predicts. The electron, the photon, the gluon, the W and Z bosons, the Higgs boson, every key piece of the standard model was found in a detector. The graviton sits outside that pattern. It is almost certainly real, in the sense that a consistent quantum theory of gravity almost certainly requires it. But the universe may have arranged things so that direct confirmation is permanently beyond reach. For now, the graviton remains theoretical. Gravity remains the only fundamental force without a confirmed quantum field particle, and the universe keeps most of its mass in a form even further from detection. Because roughly 85% of the matter in the universe does not interact with the electromagnetic field at all. It cannot be seen, it cannot be touched. But its gravity shapes every galaxy that exists. In the 1970s, astronomer Vera Rubin measured the rotation speeds of stars at different distances from the centre of a galaxy. What she found disagreed completely with every prediction. Stars far from the galactic centre should move slowly, the same way the outer planets of the solar system move slower than the inner ones. Jupiter moves much slower than Mercury. That pattern follows directly from how gravity weakens with distance. If the visible stars and gas of a galaxy contain most of its mass, the outer stars should be moving slowly. They were moving just as fast as the inner ones. The only explanation that fit the data was that galaxies contain far more mass than the visible stars and gas account for. A massive invisible halo of matter surrounds every galaxy, extending far beyond the visible disk, providing the extra gravitational pull needed to keep the outer stars moving at the speeds observed. Rubin called this missing mass. Others eventually called it dark matter. Decades of independent observations confirmed it. The way light bends around galaxy clusters, the pattern of temperature fluctuations left over from the early universe, the rate at which galaxies cluster together over billions of years, all of these measurements point to the same conclusion. The universe contains roughly 5 times more dark matter than ordinary matter. Of all the matter in existence, visible ordinary matter, everything made of standard model fields, makes up only about 1/6 of the total. 5/6 of all matter in the universe belongs to a field or particle that nobody has identified. Dark matter does not emit light. It does not absorb light. It does not interact with the electromagnetic field at all. It interacts with gravity, which is how we know it is there. It may interact with the weak nuclear force at some level, but decades of experiments designed to detect that interaction have found nothing. Physicists have built detectors deep underground, shielded from cosmic rays by miles of rock, filled with ultra-pure materials cooled to fractions of a degree above absolute zero, hoping to catch a dark matter particle colliding with an ordinary atom. No confirmed detection has ever been recorded. Scientists have smashed particles together at the Large Hadron Collider at energies never before achieved, looking for new field ripples that might correspond to dark matter. Collision after collision has produced only standard model particles. Whatever creates dark matter, its field does not produce detectable ripples at the energies currently available. Some physicists have proposed that dark matter consists of heavy particles called weakly interacting massive particles, which the equations of certain beyond standard model theories predict. Others have proposed ultralight particles called axions. Others have proposed that dark matter is made of primordial black holes formed in the early universe. Each proposal comes with specific predictions. Each prediction has been tested. None has been confirmed. The gravitational evidence for dark matter is overwhelming. The particle or field responsible for it remains completely unknown. You live inside a dark matter halo right now. The Earth and the entire solar system drift through a cloud of dark matter, roughly 1,000,000 times less dense than air. Occasionally, in theory, a dark matter particle passes through your body. It feels nothing, and you feel nothing. The interaction, if it happens at all, is far too weak to register. Dark matter is the largest confirmed mystery in physics. And it is not alone, because something else is pushing the universe apart at an accelerating rate. Something with even less explanation than dark matter. Something that fills all of space and acts exactly like a field, but matches nothing in any theory. In 1998, 2 independent teams of astronomers measured the distances and speeds of exploding stars in distant galaxies. They expected to find that the expansion of the universe was slowing down. Gravity pulls matter together. An expanding universe should be decelerating under the gravitational pull of all the matter in it. Both teams found the opposite. The expansion of the universe is speeding up. Galaxies are flying apart from each other at an increasing rate. The farther away they are, the faster they are receding. And that recession speed is growing over time. Something is pushing space itself apart and doing it with increasing strength. That something is called dark energy. Dark energy constitutes roughly 68% of the total energy content of the universe. Dark matter makes up about 27%. Ordinary matter, everything in the standard model, everything made of the fields physicists have mapped, makes up about 5%. 5%. The framework that physicists spent a century building, the most precisely tested theory in history, accounts for 5% of the universe. The rest is completely unknown. Dark energy behaves as though empty space has an intrinsic energy. Every cubic inch of space, even completely empty space, carries a fixed amount of energy. As the universe expands and creates more space, more dark energy appears. This growing energy drives the acceleration. The more space exists, the more dark energy exists, and the faster expansion accelerates. This is consistent with a mathematical term that Einstein himself introduced in his equations of general relativity and later called his greatest mistake. He added a cosmological constant to make the universe static rather than expanding or contracting. When Edwin Hubble discovered that the universe is actually expanding, Einstein removed the constant. Decades later, dark energy brought it back. The cosmological constant describes exactly the behavior of dark energy. The problem is explaining where it comes from. Quantum field theory predicts that the vacuum of space should carry energy from the constant fluctuations of all the quantum fields filling it. When you calculate how large that vacuum energy should be, you get a number roughly 120 orders of magnitude larger than the observed value of dark energy. 120 orders of magnitude is 10 multiplied by itself 120 times. It is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science. Something cancels almost all of the predicted vacuum energy. Physicists do not know what. The tiny remnant that survives is dark energy. Why the remnant is exactly the size it is, small enough to allow galaxies to form, but large enough to drive accelerating expansion, nobody knows. Dark energy is accelerating the expansion of the universe at this moment. In roughly 100 billion years, distant galaxies will be receding so fast that light from them will never reach us. The observable universe will shrink to the Milky Way and its nearest neighbours. Every other galaxy will be permanently invisible, pulled beyond the horizon of light. The fields of the Standard Model cannot reach dark energy. Dark matter. The quantum theory of gravity. These three gaps in our knowledge are not small details. They are the majority of reality, and some physicists have begun asking whether space-time itself, the stage on which all of this plays out, is as fundamental as it seems, or whether it too emerges from something deeper. Every theory of physics so far has assumed that space-time is the background, the fixed stage on which particles move, fields vibrate, and forces act. You might adjust what happens on the stage, but the stage itself is given. It is the starting point. A growing number of theoretical physicists believe this assumption is wrong. They propose that space-time itself is emergent, that it is not the foundation, but a large-scale pattern that arises from something more fundamental at smaller scales. Just as the smooth surface of water emerges from the collective behaviour of trillions of individual molecules, the smooth fabric of space-time may emerge from a web of more elementary relationships that have no obvious spatial structure at all. One of the strongest hints for this idea comes from black holes. When matter collapses into a black hole, information about what fell in appears to be destroyed. A glass bottle falls in, and no information about the bottle seems to escape. This conflicts with quantum mechanics, which states that information is never destroyed, only scrambled. The conflict between black holes and quantum information is called the black hole information paradox. One proposed resolution involves a mathematical relationship called holography. Physicists discovered that the quantum information on the two-dimensional surface of a black hole completely encodes everything happening in the three-dimensional volume inside it. A three-dimensional region of space can be fully described by information living on its two-dimensional boundary. This holographic principle suggests that the three-dimensional space inside is in some sense derived from the two-dimensional boundary. Space itself in this picture is not primary. It emerges from the boundary's quantum information. This idea extends beyond black holes. In certain mathematical frameworks, a gravity-free quantum field theory living on the boundary of a region and a quantum gravity theory living in the bulk of that region are mathematically equivalent. They describe the same physics in two completely different languages. One has space and gravity, the other has no gravity and lives in fewer dimensions. Either description is complete. If they are equivalent, then the spatial dimensions and gravity in one description are not more real than the boundary description without them. Space becomes a derived concept. Another approach comes from studying how quantum entanglement builds the structure of space-time. When two regions of space are connected, the quantum fields in them are entangled. Cut the entanglement, and the connection between the regions weakens. Some theorists believe entanglement is not a consequence of spatial connection, but its cause. Space is knitted together by entanglement. Regions that share strong quantum correlations are close to each other. Regions with weak correlations are far apart. Distance itself becomes a measure of field entanglement. These ideas are not yet complete theories. They are frameworks, some of them mathematically rigorous, some speculative, none of them experimentally confirmed. But they point toward a possibility that would change everything. If space emerges from something deeper, then the fields that physicists have been mapping inside spacetime may themselves be secondary descriptions. The truly fundamental layer might be something that has no location at all in the usual sense, something for which our words for space and time simply do not apply. Everything physicists know, every field, every force, every particle, might be the surface appearance of a structure so different from current concepts that describing it requires mathematics not yet invented. And the machine humanity built to probe the deepest structure of the known fields is the largest and most complex scientific instrument ever constructed. Beneath the French and Swiss countryside, buried 300 feet underground, runs a circular tunnel nearly 17 miles around. Inside that tunnel, two beams of protons travel in opposite directions at speeds so close to the speed of light that they complete the full circuit over 11,000 times per second. When those beams cross, individual protons collide. Each collision happens at energies never before achieved in a laboratory setting, for a fraction of a second smaller than any meaningful comparison can capture. The energy concentrated in that tiny collision point exceeds conditions that existed microseconds after the Big Bang. The Large Hadron Collider was built to do one thing: give quantum fields enough energy to produce ripples they would normally never form. Every new particle ever discovered at an accelerator was a field ripple that required more energy than previous machines could supply. Each generation of larger, more powerful colliders revealed new layers of the field structure of the universe. Building the collider required contributions from over 10,000 scientists, engineers, and technicians from more than 100 countries. The magnets that steer the proton beams must maintain temperatures colder than outer space to operate. The detectors that capture the collision products are structures the size of apartment buildings, assembled from millions of precisely manufactured components, designed to measure the trajectories, energies, and identities of hundreds of particles simultaneously in the microseconds following each collision. The collider runs millions of collisions per second. The detectors produce more raw data per second than all the internet traffic in the world combined. Vast computing networks spanning multiple continents filter and analyze that flood of data in real time, looking for patterns that match the signatures of undiscovered fields. The collider's greatest confirmed achievement was detecting the Higgs boson in 2012 after a search lasting decades, but the data collected since then has revealed something equally important and far less celebrated. The standard model keeps winning. Every new result matches its predictions. No new fields have appeared. No unexpected ripples have shown up in the data. This is simultaneously a triumph and a frustration. A triumph because the theory works. A frustration because physicists expected the energy scales probed by the collider to reveal physics beyond the standard model. New fields, new particles, new forces that would explain dark matter and other gaps. The collider has found none of it. The machine has not failed. Its measurements are extraordinary. But the universe has kept its deeper structure hidden at the energies explored so far. Proposals for even larger colliders exist. A circular tunnel roughly 60 miles around has been proposed, which would reach energies roughly 10 times higher than the current machine. At those energies, fields that produce no ripples in current experiments might finally vibrate. Dark matter candidates might appear. The structure of the Higgs field at high energies might reveal cracks in the standard model. The price is enormous. The engineering challenges are immense. The political will across multiple governments and funding agencies needed to approve it is uncertain. But the history of particle physics is the history of building machines that seemed too large and too expensive, and each time, the universe revealed something worth the effort. The discovery that justified the current machine arrived 50 years after the theory that predicted it. The discovery that justifies the next machine may already be written in mathematics waiting for confirmation. And one of those mathematical proposals, the most ambitious and controversial in modern physics, attempts to explain not just one missing field, but all of them at once. By replacing the concept of a point-like field ripple with something that extends through space in a new way. July 4th of 2012 began like most days at the laboratory near Geneva. Scientists had been working for years, some of them for entire careers, toward a single moment. The control rooms were crowded. People stood in hallways watching screens. Thousands more watched via video link from institutions across the world. The spokesperson for one of the two main detector teams stood before a room packed with physicists and began presenting the data. Within the first few slides, it was clear. A signal had appeared in the data at the expected mass. The peak was sharp. The statistical significance was high enough to meet the standard for a formal discovery in particle physics, a threshold so demanding that it allows fewer than 1 in 3.5 million chances of the result being a random fluctuation. The spokesperson's voice broke slightly as he finished presenting. People in the audience wept. Peter Higgs, then 83 years old and sitting in the front row, wiped his eyes. He had written the equation predicting this field in 1964. 48 years had passed. He had lived long enough to see it confirmed. What made the reaction so emotional was not just the discovery of a new particle. It was the confirmation of an idea that had seemed almost too strange to be real. The Higgs field had always been the most unusual part of the Standard Model. Every other quantum field sits at zero energy in its lowest state. The Higgs field does not. It sits at a non-zero value everywhere in the universe at all times. It never turns off. It fills all of space permanently. This is called a non-zero vacuum expectation value, and nothing like it had ever been proposed for any other field. It was the feature that gave the theory its power to explain mass, and it was also the feature that made physicists most suspicious of it. A field that cannot be switched off seemed like an ad hoc addition, a mathematical patch rather than a physical reality. The boson confirmed the field. A field with a non-zero vacuum expectation value must produce a specific type of ripple when disturbed enough. That ripple is the Higgs boson. Finding it with the predicted properties confirmed that the Higgs field is real, permanent, and universal. Every time you push an object, you are feeling the Higgs field at work. The resistance of mass to acceleration is the resistance of field ripples moving through the Higgs field's permanent non-zero background. Your weight when you step on a scale is the Higgs field measured in kilograms. But the discovery also opened new questions. The Higgs boson is extremely unstable. It decays almost instantly into other particles. The rate and pattern of those decays reveal details about how the Higgs field couples to other fields. Precise measurements of those decays might show small deviations from standard model predictions. Deviations would be signs of new physics, new fields, new interactions not yet in the theory. So far, the decays match predictions. No deviations have been found. The Higgs field is real. The mass-giving mechanism is confirmed. The universe has exactly one fundamental field that cannot be switched off. And that permanence, that inability to ever reach a true zero-energy state in the Higgs field, raises a question that connects to everything from the Big Bang to the long-term fate of all matter. Whether the Higgs field as it exists today is truly stable, or whether it sits in a state that could, under the right conditions, suddenly change. Everything discussed so far treats field ripples as point-like. An electron is a localized excitation of the electron field at a point in space. A quark is a localized excitation of a quark field at a point. The Standard Model treats all particles as zero-dimensional points with no internal structure. String theory proposes something different. What if the fundamental objects are not points but tiny one-dimensional filaments of energy, strings so small that the entire observable universe would need to be magnified by a factor larger than the distance from Earth to the nearest star just to see one. Each string vibrates. Different vibration patterns produce different particles with different properties. An electron corresponds to a string vibrating in one pattern. A quark corresponds to a string vibrating in a different pattern. A photon corresponds to another pattern. And crucially, one specific vibration pattern produces a particle with exactly the properties a graviton must have. String theory automatically includes gravity. Every other approach to quantizing gravity has produced unresolvable mathematical problems. String theory avoids those problems because the extended nature of strings smooths out the singularities that cause point particle calculations to blow up. When you try to calculate a gravitational interaction using point particles, you get infinities. When you use strings, the calculation produces finite, sensible answers. This is string theory's most powerful feature. It is the only known framework that combines quantum mechanics and general relativity without producing mathematical nonsense. The price of this feature is steep. String theory requires extra dimensions of space beyond the 3 we experience. Depending on the version, 6 or 7 extra dimensions are needed. These dimensions are curled up so tightly at scales far smaller than an atom that they have no observable effect at energies accessible to any current or planned experiment. The specific way these extra dimensions curl up determines the physical properties of the universe, the masses of particles, the strengths of forces, the value of dark energy. There are an enormous number of ways the extra dimensions can curl. Some estimates put the number of possible configurations at 10, followed by 500 zeros. Each configuration describes a different universe with different physics. Ours is one of them. Finding a principle that selects which configuration produces a universe like ours has not been achieved. String theory also requires that every known particle has an unseen partner particle, called a supersymmetric partner, with different spin but otherwise related properties. These partner particles, called sparticles, should have appeared in collider experiments if their masses are in the range the theory initially suggested. Searches at the Large Hadron Collider have found no sparticles. None. This has forced theorists to push their predicted masses into ranges that the current machine cannot reach. String theory has produced extraordinary mathematics. Insights from string theory have advanced pure mathematics, led to breakthroughs in understanding black holes and quantum information, and generated the holographic principle discussed earlier. But it has produced no confirmed experimental prediction. After more than 50 years of development, it remains a mathematical framework, extraordinarily rich, internally consistent, deeply connected to other areas of physics, but not confirmed by any experiment. It may be right, it may be wrong, it may be a piece of the right answer. The honest position is that nobody knows. What is certain is that the current framework, powerful as it is, leaves the deepest questions unanswered. And one of the deepest questions of all sits at the boundary between physics and the thing you are doing right now as you process these words. Every idea in this story so far has been confirmed by experiment derived from mathematics, or clearly labelled as theoretical but constrained by physics. This chapter is different. Consciousness is the hardest problem in all of science. You know you are having an experience right now. You know there is something it feels like to be you, to hear these words, to feel curiosity or confusion or wonder. That's subjective experience. The inequality of awareness has no accepted physical explanation. Physicists, neuroscientists, and philosophers have made essentially no progress on explaining why physical processes in the brain produce subjective experience at all. This gap has led a small number of serious physicists and researchers to propose something radical. What if consciousness is not produced by the brain, but is itself a fundamental feature of the universe? What if awareness, like mass or charge, is a property associated with certain field configurations? One version of this idea was proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggested that quantum processes inside structures in brain cells called microtubules play a role in consciousness. Microtubules are protein structures inside neurons that help maintain cell structure and transport molecules. Penrose and Hameroff proposed that quantum field states inside these microtubules achieve large-scale coherence, and that the collapse of these quantum states is what generates conscious moments. Most neuroscientists are skeptical. The brain is warm, wet, and noisy. Quantum coherence of the kind needed by the theory normally requires extremely controlled conditions, near absolute zero temperatures and isolation from any environmental disturbance. Maintaining quantum coherence in biological tissue for long enough to be neurologically relevant seems extremely difficult. Experiments have not confirmed the mechanism. A broader class of ideas, called panpsychism, proposes that consciousness or proto-conscious properties are fundamental features of reality, present to some degree in all physical systems and not emergent from any specific arrangement of matter. Under this view, the fields of physics might carry some form of raw experiential quality at every scale, and human consciousness represents a highly organized integration of these fundamental properties. These ideas are controversial. Most physicists and neuroscientists regard them as premature at best. There is no mathematical framework for consciousness as a field. There is no experimental signature to test. There is no prediction that distinguishes these proposals from alternatives. But the hard problem of consciousness is real. Explaining why any physical process produces subjective experience remains completely unsolved. Every physical theory to date describes what systems do without explaining why there is something it feels like to be a system doing it. That gap exists. No existing field theory fills it. Whether a future physics will include something like a consciousness field, or whether consciousness will turn out to emerge from known physics in a way not yet understood, nobody knows. The honest answer is that the inner experience you are having right now, the awareness processing these ideas, is the most immediate and undeniable fact in your life. And physics has no account of it. And that gap between the richness of inner experience and the equations that describe fields and forces brings the entire story back to the most direct and personal implication of all. Every atom in your body was forged inside a star. The carbon in your cells, the oxygen in your lungs, the iron carrying oxygen in your blood, none of it was created on Earth. Stars fuse hydrogen into heavier elements over millions of years. When a massive star exhausts its fuel, it collapses and explodes in a supernova, scattering those elements across space. That scattered material drifts for millions of years, condenses into new solar systems, and eventually finds its way into planets, into oceans, into living things. You are made of exploded stars. Every atom in your body has been recycled through at least one stellar furnace. But go deeper than atoms. Go to the level of fields. Every atom in your body is a set of quantum field ripples. Your electrons are vibrations in the electron field that covers the entire universe. Your quarks are vibrations in quark fields. The forces holding your atoms together are produced by the electromagnetic field, the strong force field, the weak force field, all of them universal, all of them stretching from inside your cells to the edge of the observable universe. You are not a collection of objects. You are a pattern. A temporary, extraordinarily complex arrangement of vibrations in fields that existed long before you were born and will continue long after every atom that currently makes up your body has moved on to be part of something else. The atoms in your left hand were somewhere else a few years ago. The atoms will be somewhere else again in a few more. The pattern persists, but the material flowing through it is always changing. You are more like a wave than a particle. You are a stable ripple in the ocean of reality, maintained by the continuous flow of energy through the quantum fields that make you. And here is the thought that should sit with you. Every electron in the universe is a vibration in the same field. Your electrons are not separate from the electrons in the Sun, in distant galaxies, in the cosmic microwave background radiation left over from the Big Bang. They are all ripples in the same universal electron field. At the deepest level, there is no boundary between you and the rest of the universe. The boundary is a feature of scale, not of physics. Quantum entanglement connects field ripples across any distance. Every particle you have ever interacted with left a trace of entanglement in the quantum state of your body. Every photon your eyes have ever absorbed, every molecule of air that has ever passed through your lungs, every food molecule that has ever bonded with an enzyme in your digestive system, each interaction left a quantum correlation. The entanglement web connecting you to the rest of the universe is vast. Physics does not tell you what to make of this emotionally. It simply describes what the equations say. What the equations say is that you are not separate from the universe observing it from the outside. You are the universe observing itself from the inside. A temporary pattern in fields that are as old as time, using quantum interactions to process information about the larger pattern you are embedded in. The solid world you experience is real. The separateness you feel is real at the scale you live at. And below that scale, the deepest physical description available says the separateness dissolves. Fields all the way down, connected all the way across, vibrating still.